All right. Well, good morning, folks. Hopefully, welcome back. I want to go ahead and I want to get into the discussion right away and try to finish up with this discussion of liquids today, and then try to get through with the or start the discussion of solids, and hopefully get done with the discussion of solids tomorrow, so we can go ahead and get started with the chapter 14 material as well. So as it looks now, I think we are good to go to meet on Friday. Like I said, if anything comes up, I will let you know. I'll post the the Zoom Meet information for us on Classroom, and that was then we go ahead and meet at that point. We'll meet for a little bit. I want to see if I can take some of your questions, and then I'll let you go to watch the video for the day. But I just want to go ahead and I want to check in with you folks on Friday. So Friday during our class periods. So we'll meet for a few minutes beforehand, just to kind of see how people are doing, and then I'll dismiss you, and then you can go ahead and watch the videos for that day, for that period. Okay. So if if there are changes that occur, I'll let you know. But I'm looking forward to meeting you folks on Friday. Okay. All right, let's pick up where we left off with on yesterday, and we were talking about evaporation. We were finishing up our discussion of evaporation. I was mentioning then that the process in which a liquid becomes a gas, the general process is known as vaporization. Vaporization can be occurs in two different ways. It can occur by evaporation, or it can occur by boiling, and we're going to talk about boiling next. The key difference between evaporation and boiling, you can notice that there is a noticeable difference that you can observe. Okay, and so we'll talk about that. But the key difference between evaporation and boiling comes down to heat, the amount of heat that is applied to the liquid itself. Okay, and so what you need to make sure you understand is both require heat, but they just require different amounts of heat. And as a result, then what you'll see then is that the way that the vaporization occurs will be very different between the evaporative process and the boiling process. Okay, so let's continue then with the evaporative process, and let's talk about that, and let's review that really quickly. So with evaporation then, the vaporizing liquid particles vaporize at the surface of the liquid itself. So at the surface of the liquid itself, you have particles, liquid particles that are moving around. We said then liquid particles move around. They have these attractions for one another, but the particles at the surface, there's no liquid particles above them to hold them down. So at the particles at the surface have interactions. They have attractions to particles on their sides. They have attraction to particles below them, but there's nothing above them to hold them down. Everything else below them, so you can imagine the particles at the surface, everything else below them has something above, has another particle above that holds them in place, but not at the surface. So at the surface then, as these particles move around, a few of them, as they move around, will acquire enough kinetic energy, meaning then they start to move faster. They acquire enough energy and they move fast enough where they can break free of those attractions. And as soon as they break free of those attractions, remember, the key characteristic, the key difference between the liquid particles and the gas particles is that there are attractions. And so if the liquid particle at that point breaks free of all of its attractions, then what is it but a gas particle? And there we have the transition of a liquid particle to a gas particle, and there it is. That's the process of vaporization, but at the particle level. Okay, so we can observe vaporization. We can see the liquid level drop as the liquid evaporates, or when the liquid boils. But when the liquid evaporates, we can observe that. We can see the liquid itself, the liquid level drop. But what's happening at the microscopic level is that these particles then are breaking free of their attractions for one another. And this only occurs at the surface now. And as they break free of their attractions for one another, they then become a gas particle. So there it is. So that's how evaporation works. And evaporation, again, only occurs at the surface of the liquid itself. So you got to make sure you remember that as you move forward. Okay. All right. So with that said, then, as you add more heat to a liquid, and the way that I wanted you to think about this yesterday was that imagine taking two pots of water, placing one inside the refrigerator and one outside, okay, putting it outside on a hot day. Okay. You will notice then that the liquid level will drop much faster for the pot of water that is sitting outside than for the pot of water that's sitting inside the refrigerator. Why is that? Water is water, so it would evaporate at the same rate regardless. But the key difference then is the temperature. That is the amount of heat that each pot of water feels. The pot of water in the refrigerator does not have as much heat. There's not as much heat in that refrigerator. That's why it's cool. So the temperature is lower. So there's less heat energy inside the refrigerator. Outside of the refrigerator, it's warmer. The temperature is higher. So there's a lot more heat energy that's floating around. And so what happens is that heat energy gets absorbed into the pot of water itself. The water absorbs that heat. And as it absorbs that heat, it will start to evaporate. But keep this in mind, what I just said there, that the water absorbs heat, meaning then that it's taking heat from the air. It's taking heat from the air. And that is why yesterday I ended up by talking about how evaporation is a process that cools down the environment. Evaporation is a process that requires heat. It requires heat, but what the liquid does is it absorbs it. It sucks the heat in from the atmosphere. It sucks the heat in from the atmosphere, and as a result, it cools down the environment. And so, is it noticeable? A lot of times it's not. It's not. However, it is noticeable when that evaporation takes place on you. When you sweat, the sweat on your that you produce allows you to cool down much more efficiently than if you didn't. So the sweat that you have, that you produce when you're running, when you're exercising on a hot day, allows you to cool down much more efficiently, because as the sweat evaporates, as the liquid water particles evaporate, it's removing heat from your body, thus bringing down the temperature in your body. So you will feel that cooling process as the sweat evaporates. And so when the wind blows on you, it feels much cooler because it's causing that evaporation to occur much faster. Okay? That we don't talk about in this class here. We talk about later. But do you understand then that evaporation requires heat? It's a process in which the liquid requires heat. But as the liquid acquires that heat from the surroundings, it cools down the surroundings itself. And so therefore, when we talk about evaporation as being a cooling process, that's exactly what we mean. Okay, that's how we explain it. Okay? So as evaporation occurs, the liquid, the remaining liquid temperatures decrease. Okay, and so what happens is it starts to absorb more heat energy, and as it absorbs more heat energy from the environment, it cools down the environment. Okay, the evaporation is a cooling process, and let me specify here: it's a cooling process in which the surroundings go down in temperature. So as the water absorbs heat, it causes the surroundings then to go down in temperature, the surroundings to cool down. Okay, all right, very good. So that's something I wanted to point out to you, because it's something that's very interesting that seems almost counterintuitive, but it does work. Okay, so let's go ahead and let's take a look at what's happening here at the microscopic level. Okay, and so what happens, you can imagine, here's your water droplet. Okay, so you have a water droplet here. Okay, and so what happens is this water droplet has water particles that sit at the surface. Remember, that sits at the surface, and here's a water particle that sits at the surface of this water droplet here. Imagine that's a sweat bead that's on your head. Okay. So the sweat bead then is going to absorb heat from your body, from your head. The sweat bead is going to absorb that heat from your head. Okay? And as it absorbs heat, the water particles that sit at the surface here, they leave. They leave with all that kinetic energy that they absorbed. Now remember, kinetic energy is proportional. Kinetic energy is proportional to temperature. So if which is proportional to heat. Which is proportional to heat. So if the particles leave with a lot of kinetic energy, it's at a higher temperature, it's going to take with it a lot of heat. And so what happens is everything else, the surroundings here, will lower the temperature, because effectively what's happening here is it's losing heat. It's losing heat, and as it loses heat, the temperature drops. Okay? And so that's what I want you to keep in mind as you move forward, and that the process can easily be explained, okay, at the molecular level. So the evaporation, high kinetic energy particles, they will leave, the molecules will leave, okay, leaving behind lower. So you can imagine when this particle leaves right here, what's left over, okay, what's underneath, and what's left over then is going to be another water particle. Okay, waiting in the wings, ready to go, but it is not fast enough. It doesn't absorb enough energy. But once it gets to the surface there, it's going to start to absorb more heat energy, and it leaves. And the process continues until the water droplet evaporates completely. Okay, and so low energy molecules are left behind. Those low energy particles then will absorb heat, and then they too will leave, and thus removing with them the heat energy. Okay, so that's how evaporation absorbs the latent heat, and then it cools down the surroundings. Okay, so evaporation cools down the surroundings by absorbing heat energy from the surroundings. Okay, so make sure you keep that in mind. Okay. All right, very good. So let's go ahead then. That's it for evaporation, folks. So we've talked about evaporation, and so that's one property of liquids that we have to consider. Now, do understand this: different liquids evaporate at different rates, and so there is other factors that determine then how quickly a liquid evaporates as well. So we've only talked about one factor. We were talking about energy. We were talking about heat energy. So there are other factors that determine how quickly a liquid will evaporate, but we'll leave that discussion for a later day. Okay, or we'll leave that for we'll talk about one other factor in just a moment. Okay, but evaporation depends on the properties of the liquid itself. So water evaporates at a certain rate. But you compare that to gasoline, for example. Gasoline's a liquid; it evaporates much more quickly. Okay, so but compare that to glycerin, or say compare that to thicker liquids, and oil, for example. That's somewhat a liquid, and it takes longer to evaporate. So the properties of the liquid itself will also determine the rate of evaporation. So it's not just temperature; it's also the properties of the liquid itself. Okay, all right. So with that said, then let's turn our attention then to a second property. The second property that liquids possess, and that is this idea of a vapor pressure. Vapor pressure, folks, even though the term vapor appears in the name, vapor pressure is a property of liquids. Different liquids will have different vapor pressures. Okay, and so what you want to make sure you keep in mind is, and this is something I will remind you of often, and you'll have to remember that whenever we talk about vapor pressure, it's the pressure that's generated by a liquid as it evaporates. It's the vapor pressure. It is the pressure of the gas. So it is the gas, but it is the gas that forms. It's the vapor that forms when the liquid evaporates. So different liquids evaporate at different rates. I've just mentioned that, and because of that, different liquids will have different vapor pressures, and we can use that vapor pressure to identify the differences between different liquids. And so you can imagine here. So the vapor pressure is the measure of the pressure exerted by a liquid. Okay, the pressure exerted by a liquid as it starts to evaporate. So you can imagine here, and we'll talk about this in just a moment, just real quickly. You have a liquid here. We have it in a bell chamber. It's a vacuum. So if it is a vacuum up here right now, you can imagine that the pressure is going to be 0. And we'll use atmospheres for now, but hopefully you can convert that to millimeters of mercury and kilopascals. But and so atmosphere is probably more common. You'll notice that as you move on, atmosphere is more commonly used than any other pressure unit. But initially, we have this in a bell chamber. We have it in a vacuum chamber, which means then the pressure is initially 0. And the only thing in this container then is the liquid. Soon, if you what you'll notice start happening is that pressure starts to increase. Okay, and so here then, let's say then the pressure then is going to be half an atmosphere. Okay, so as the liquid evaporates, and so make sure you understand this: if it is a vacuum in here, the only place that the pressure can come from, remember, pressure is exerted by a gas. So the liquid doesn't, we're not measuring the liquid pressure. The liquid also exerts pressure in itself. But you can imagine then we can place a digital barometer up here, and it can measure this. And we'll talk about this in just a moment. But it is the liquid particles that are pushing out, evaporating, generating these gas particles, and these gas particles that are now moving around and generating that pressure. Okay, and so what I would like to do is I want to examine this process, this phenomenon known as vapor pressure for a liquid, and then be able to explain it on both the macroscopic and the microscopic level. Because on the macroscopic level, I think it's pretty easy to see. You just have to read the dial or read the measuring device and determine then whether there's a pressure or not. Okay, so but the vapor pressure then is the force exerted by the gases produced when a liquid evaporates. Okay, so what you want to make sure you keep that in mind. Okay, all right. So let's go ahead then. Let's consider what we had. Okay, so let me explain the apparatus to you really quickly. Okay, and let me go ahead and then we'll examine. Okay, so in this apparatus here we have a chamber. So this is a chamber right here. This is a vacuum chamber. Okay, so what we've done then is we've evacuated this chamber. Okay, so it's a vacuum. Okay, and in this chamber here, all we've done is place the liquid. Let's say liquid water. Okay, this chamber is attached to a mercury barometer. Okay, so this is a mercury tube here. So the barometer here is this tube here is filled with mercury. Okay, so right now, what I'd like you to do really quickly then, just to remind us of how this works. If the chamber here right now is a vacuum, what is the pressure? What's the pressure here? What's the pressure in that column right there? Okay, so real quick, take about 30 seconds, just 30 seconds. Okay, you tell me what is the pressure in this column right here. Okay, so go ahead and do that really quickly. Okay, let's consider what we have here. Okay, let's consider what we have here. Okay, if this is a vacuum, what would the pressure be? Well, the pressure then would be 0 atmospheres. The pressure is 0 atmospheres. There is nothing pushing down on this side here. Remember how a barometer works, how a mercury barometer works. The mercury moves when pressure is pushed down on one side and the other, and then the column starts to move. We saw that with the mercury barometer. Atmospheric pressure pushes down on the mercury dish. The mercury then pushes up into the test tube inside, and we can measure the height of the mercury column as it moves. Okay, so if we notice here, then we have the mercury column, the mercury levels on both sides of this tube here being at the same level, meaning then that there's nothing pushing down on this side. Now imagine this: if this pressure was greater, if this pressure was greater than 0. Now understand, first of all, you have to get this. You have to be able to determine then that the chamber is a vacuum. The chamber is a vacuum. Pressure is going to be 0. Okay? Now, if this pressure here is greater than 0, if this pressure here was greater than 0, would these two sides of the U tube be the same? No. Remember, what happens is the reason why they're the same is that there's equal pressure on both sides. And so therefore, the pressure over here must be, and let's go ahead and do this, the pressure over on this side then now has to also be 0 atmospheres. So we start out with the condition, we'll call this initial. So this is P initial, okay? P initial at 0 atmospheres. Okay. All right. So let's take a look at what happens next. Okay. The particles. So we start. We have this apparatus set up outside at room temperature. We have it set up at room temperature. Okay. And so at room temperature, then what do these liquid particles start to do? Well, remember what happens here is that we don't have it initially, but as soon as it starts, these gas particles or these liquid particles at the surface start to absorb some of the heat, some of the kinetic energy, they start to leave. So here then we have evaporation occurring. Evaporation starts to occur, which means then we start to get gas particles here. We start to get gas particles here, and so the vapor pressure starts to increase. This vapor pressure is the pressure exerted by these gas particles here. These are gas particles. These are water vapors that are coming from the liquid. These gas particles, remember, this is a vacuum chamber. It's sealed. It's sealed. Nothing goes in, nothing goes out. Nothing goes in, nothing goes out. And so therefore, these particles here that form, these gas particles, they come from the liquid. And how do they come from the liquid? They evaporate. They go through the process of evaporation. Okay, so they evaporate, they escape from the liquid. And so let me ask you this. Simple question, but I want you to take another moment to answer this question, Kim. Okay. From the diagram then, explain from the using the diagram in your explanation, how do we know that there's pressure? What is it that we observe? So we can't see the gas particles come out. We don't see the process of evaporation, but we do notice a change in the pressure. And so the question I want to ask you here real quickly then is, tell me how you know, and use the diagram here to support your answer. Okay, so take about a minute to write out your answer, and then we'll go over, okay? All right, well, let's go ahead. And if you understood the discussion here that we had in terms of the equal pressures on this side, okay? So for right now that we have the pressure in the chamber equal to the pressure on both sides here, okay? So if you notice, and with that said then, the two sides of this column are equal. If you notice then, the right side of the column has increased. It has moved up. It has been pushed up this side here. What does the pushing, except for these particles as they come out, they come down and they push down on this side of the mercury tube right here. And as they push down, they will push the other side of the mercury tube up. And it's this difference here. It's the difference in height here from here to here. This difference in height is difference in height here. And we can use then to demonstrate that there is pressure, which means then, now that we know this, the pressure on the left-hand side, I'll change the color here just to make sure that we can differentiate here. So we'll call the blue initial pressure on the left-hand side, okay? And so they're equal to the pressure on the right-hand side, okay? And so with that said then, and I'll finish up here, folks, the pressure, now we can say then, the pressure on the right-hand side, sorry. The pressure now on the right-hand side, this is not initial pressure, we'll call this pressure 1, is going to be greater, and let's go ahead and change this really quickly, than the pressure on this side. The pressure on this side, it's still a vacuum, folks. The pressure on this side here is still going to be roughly about 0 atmosphere. So it pushes up into it. And so we have then pressure on the right-hand side, pressure on the left-hand side. The pressure on the right-hand side will be greater than the pressure on the left-hand side. Okay? And again, that's how we know that something's happening. That's how we know that there's this vapor pressure that's forming over here. So what I would like you to consider then is what's happening on the last frame here. Okay, so we talked about the initial condition here, pressures are equal. Okay, the second frame here where the pressure starts to build on the left-hand side, and so it pushes down in the column. The last question I would like to ask you then is, what's happening in this third frame here? What's happening in this third frame here? Okay, and I'd like you to answer that, and then we'll pick up with this discussion tomorrow. Okay, so what's happening in the third frame is obviously the third frame is not like the second frame. Okay, so there's differences. So explain what that difference is. Okay, so please make sure you write that down on your paper. Hold on to it. Okay, and then we'll use that to talk about how vapor pressure is, how we can determine what vapor pressure is, and how we can measure vapor pressure, and how vapor pressure changes with different liquids. Okay, so please make sure you write that down. Have it for tomorrow, and then we'll go over at that point. Okay, folks. All right. Have a good day. And I apologize. You know, I had to leave. I had to leave a little bit. I had to leave a little bit early for my office hours today. So if I missed you, I apologize. Stop on by after school today. I've set aside the whole time for office hours. So come on by if you have your questions. I know a couple of you emailed me already. So come on by and get your questions answered this afternoon. Okay. Hopefully I'll see some of you then. Okay. Have a good day, folks.